As mentioned in a previous video, all particles are constantly in motion, which means they have kinetic energy. We're now going to look at how the fact that particles have kinetic energy affects their properties. This video will look at the kinetic molecular theory, specifically how it applies to gases and describes the behavior of those gases. The kinetic molecular theory of gases makes these 6 assumptions, and those assumptions help to explain the basic characteristics of gases that we see over here. In this video, I'm going to go through each of the assumptions of the kinetic molecular theory of gases individually, and then at the end we'll talk about how those assumptions help to describe the basic characteristics of the gases that we see over here. The first assumption of the kinetic molecular theory of gases is that all gases are made up of tiny, submicroscopic, so we can't see them, particles. The particles are atoms or molecules. Notice that these are not going to be ions. We generally do not see ions in the gaseous state. This aspect of the theory is fairly easy to understand. There are small particles that we cannot see that cause gases to behave the way that they do. Again, these can only be atoms or molecules. Later in Unit 2, we're going to talk about what ions are and probably give you an idea of why they can't be in the gas phase. Essentially, this is saying that gases are made up of lots and lots of little parts, and it's not just one big giant thing that we breathe, but it's made up of a whole lot of small parts. The second assumption that we make is that the gas particles are constantly moving with high velocities. They're going in straight lines, they're going in every direction, and they're colliding frequently with each other and colliding with the walls of the container. The first part of this statement, the gas particles are constantly moving, should be no surprise because, as we said, particles are constantly in motion. All particles are always in motion. The second one says that they're moving with high velocity. That means that they're going very fast, and that means that they have high kinetic energy. No matter what the particle is, in the gaseous state it has a lot of kinetic energy. That's how it stays a gas. Next it says that they're moving in straight lines. So these are like those wind-up toys that you find at a gift store, and they just keep going straight, and they go straight until they hit something. Once they hit something, then they flip around and they go back the other direction. That's the type of motion that the gas particles have. So this is saying that those gas particles are following Newton's first law, or something called the law of inertia, which says that objects will continue in the same direction until they are acted upon by a force. The fact that these particles are colliding with each other, and especially the walls of the container, mean that they have pressure. So they are constantly pushing outward because they're crashing into the walls of the container. This also tells us that that pressure is exerted in all directions because the particles are moving in all directions. Next, we can see that the distance between the particles is very large compared to the size of the particles themselves. To get a concept of what I mean by this, you might think of it like 2 people are in a football stadium with all the seats and everything else, and they're trying to walk in one direction, and they just keep going in that direction until they collide with somebody or something else. So how often does that happen? Well, it's pretty rare. They actually don't bump into each other very much because they have this large distance between them. And the next part of the kinetic molecular theory of gases is that the gas particles have no appreciable attraction for each other. What that means is that when they do collide with each other, if they do collide with each other, they just bounce off of each other and go in the other direction. So when they collide, they go in another direction. This would be similar to something you might see like a billiard ball. So you're playing billiards, pool, something like that. You're shooting the ball and it just hits another ball and then bounces off in another direction. They do not stick together. And that leads to the next assumption of the kinetic molecular theory of gases, and that is that the collisions between the gas particles are perfectly elastic. Therefore, there is no net loss of energy as the result of any collision that does occur. So what do we mean by perfectly elastic? That's a little bit hard to understand. Elasticity in this case means that it bounces back with the same amount of energy. Again, here you might think of something like billiards, where you shoot the ball, they crash into each other, they crash into the wall, but they continue to move until they're acted upon by another force. Now, in the case of billiards, they do get stopped because there's some friction with the billiard table. But if that wasn't there, those balls would continue to move on until they crashed into something else and bounced off in one another direction. So there would be nothing to slow them down. An elastic collision says that when they bump into each other, the total energy stays the same. Now notice that doesn't mean that each particle has the same energy as it originally had. Sometimes the energy of one will transfer to the other. This is like when you hit the cue ball in pool and it is initially going quickly and then it hits a ball that is not moving. When that happens, the cue ball might stop and the other ball will continue to move. The overall energy is still the same, and that's what we call an elastic collision. In this theory, it says specifically that there is absolutely no loss of energy. That's why we call it perfectly elastic. To give you an idea of something that would be an inelastic collision, so one that loses all of its energy, would be something like throwing a pie at somebody. When you throw a cream pie at somebody, it just sticks. It doesn't move, and neither does the person. In that case, it's considered an inelastic collision because all of the kinetic energy of the pie, the one that was in motion, is lost, and it is changed all to potential energy. And the last part of the kinetic molecular theory of gases states that the average kinetic energy of the particles is the same for all of the gases, regardless of the particle mass, at the same temperature, and that value is directly proportional to the absolute temperature. And this makes sense because we know that the average kinetic energy is measured by the temperature. And we also know that as the kinetic energy increases, the temperature increases, the velocity of the particles will go faster. Now what we know is that that velocity will vary dependent upon the mass of the particle. So a smaller mass will move faster and a larger mass will move slower, but that they have the same kinetic energy overall if they're at that same temperature. All of these assumptions that we made in the kinetic molecular theory of gases will be able to help us describe the basic characteristics of these gases. So here we're going to look at 6 common characteristics of gases, and I'm going to talk about each one individually so you understand what they mean. For the gases, we know that they have no definite shape or volume, a low density, they are highly compressible, they exert pressure in all directions, they flow and they diffuse, and they expand greatly when heated. So what do we mean when we say that a gas has no definite shape or volume? Well, definite means it's defined, it's set, it doesn't change. Gases are changeable. Let's break this into 2 parts. We're going to talk about the shape first, and then we'll talk about the volume. For the shape, when you have a gas in a cylinder, you release it into a balloon, and if the balloon's shape is a standard balloon shape, that is the shape the gas will take. If it has the shape of a bear, it's going to have that shape. If the balloon has the shape of a heart, it'll be in the shape of the heart. So the gas takes on the shape of its container. It doesn't have a defined shape by itself. It takes on whatever shape it can. What about volume? Again, gases do not have a definite volume. That means it's changeable. So if I have a cylinder with helium and it's a 5-liter cylinder, about 30 1-liter balloons can be filled. And if you pop all the balloons and let the gas escape into the room, you'll have about 20,000 liters of gas. And then if you open the door and let the gas out of the room, now you'll have the whole earth filled with that gas. That gas, the helium that you put into the balloons, will now be out of the balloons and they will spread everywhere around the world. So that'll give you the volume of the air of the world. So overall, we know that a gas will fill whatever container it's in all areas, and that it will take on the shape of that container. And in this one, we're saying that gases have a low density. In this case, we're comparing that density to solids and liquids, and we know that gases are not in contact with each other, so they have to be spread apart. One of the rules of the kinetic molecular theory of gases is that the gases must be fairly far apart. Like we mentioned, two people in a football stadium, and you can see that they're very, very far apart. And so gases have a low density, and because of that, we find that if we have a solid, a liquid, and a gas of the same substance, that the gas will always be on top. Our next topic is that gases are highly compressible, and that just means that if I squeeze on a container that has a gas in it, the gas particles will get closer and closer together, but they'll still be far enough apart to be considered gases. So in my example of having two people in a football stadium, we would say that that was a gas, but we could compress them. That means we could push them closer together and say that they're now on the football field. They're still not going to be in contact with each other too much, and so we would say that they are gases. And we can push them even closer and say that there are two people running around on halfway through the field, and again, we would still get them still far enough apart. This shows us that gases can be compressed, but we have to push them together. So we have to put pressure, added pressure, to get them closer and closer together. But we know that they are still gases because they are not in contact with each other. For letter D, we see another basic characteristic of gases is that they exert pressure. And what we mean by this is that they are pushing outward at all times in all directions, so not just outward but inward. And remember that when we talk about pressure, what we're talking about are the particles hitting the walls of the container. These particles are moving around in straight lines, and they're just constantly hitting the walls of the container and each other, but mostly the walls of the container, and they're pushing outward so that we have some pressure. When you take the pressure of your tire on your bike or your car, you'll notice that you don't have to take the pressure at the top or at the bottom. Wherever you test the pressure, it's going to be the same. So it doesn't matter where you're pushing, that pressure will be the same at all times. And a basic characteristic of gases is that they flow and diffuse. These really are two separate things, so I'm going to talk about each of them individually. So when we say that something can flow, we mean that it continues on in the same direction. So when you see a river, the river flows in one direction and it just keeps going in that direction. Same thing can happen with a gas. If I have a gas inside of a container and I release the gas, it's going to shoot out of whatever opening we have, and it's going to go in that same direction fairly continuously. So all of the particles will continue to go in that direction, and we call that flowing. When we talk about diffusion, we're actually talking about something slightly differently, and diffusion means that they spread out. So gases spread out in various directions. If we release a gas and it goes out in one direction, we know that it's flowing, but what happens is those particles start to bump into each other and into other gas particles that are around them. As they collide with each other, they start to go in different directions, and we'll see that we now have a diffusion effect. So when something is diffusing, that means it's spreading out into other areas in different directions. Now we know that if we release a little gas at the front of the classroom, and of course I mean some perfume, that scent will go to the back of the room eventually. But we also know that the front of the room will smell it very strongly, and at the back of the room it'll get weaker and weaker until it's very spread out. And when we open the door, those gas particles will go out the door, and they'll be out throughout the world. But then they'll become so diffuse that we won't smell them anymore. And our last basic characteristic of gases is that they expand greatly when heated. And this just means that as I heat them up, they get bigger and bigger and spread out further and further away because they are moving faster. Remember that when we add heat to something, the temperature rises, which means that the kinetic energy is increasing. So those particles are moving faster. They're pushing out on the container that they're in, and they're going to expand. Now this has to be in an expandable container. So if I'm in a cylinder, even if I heat it, that cylinder cannot expand. But if I'm in a balloon, the balloon can get larger and larger. So that's what we see with a hot air balloon. If you continue to heat the gas cylinder, though, it will try to expand, and it will increase its pressure instead, and it will eventually explode. So that's why we don't ever put a gas cylinder into something where it would be heated. So that's all about the kinetic molecular theory of gases and the basic characteristics of gases. In the next video, we're going to talk about the gas laws, which tell us how those properties and the kinetic molecular theory of gases affect those properties when we change things. We're going to call that the gas laws. After that, we'll talk about the kinetic molecular theory and basic characteristics of liquids, and then the kinetic molecular theory and basic characteristics of solids, and do a comparison of all three, the gases, the liquids, and the solids.